This always happens. All right, let us pray. Heavenly Father, we thank you for this day. We thank you for the reasonably good air quality in this room, and that we're not on the third floor right now. I just pray that you'd help us to focus on physics and to learn a little bit more today, Lord. In your name we pray. Amen. Oh man, have you guys been up on the third floor lately? Yeah. Maybe, I don't know, maybe where you are it's not bad, but close to, I just skipped lunch in my office because I just don't want to be there and breathe that. And the stairwell's really bad. It's like, I don't know if it's gas or burn oil or what, but there's definitely fume. Yeah, it seems like exhaust, yeah. I'm quite certain I shouldn't breathe it. I don't know what it is. I just know that my body is telling me, do not breathe this over a sustained period of time. If it's that thick in physics lab, I will cancel lab. Amen. So, pray for fumes. Wait a minute, no, pray the fumes dissipate so we can have physics lab. What am I saying?
Safety first. Does that apply for Dinsmore as well?
Dr. Dinsmore is made of tougher stuff. He was once in the military, you know. Let's see here. I am but a weak civilian. All right. Any questions about any problem in particular? Otherwise, I'm just going to start carving my way through them again. To let you know where we're going, next class is energy analysis. That's basically lecture 18 in the lectures I have posted. Energy analysis is itself very interesting, has really neat applications in chemistry and other things. But, I mean, everything we're doing is sort of energy analysis, but, you know, anyway, you'll see that next class. So, in next class, I'll solve the spring force problem also, and I'll prove that energy is conserved for a spring as long as there's no friction. So, is there any question in particular you have you'd like to see me work through in homework 6 or 7? Oh, so you guys did so well on the last test that you don't need to work ahead. That's good. Good. Okay. I get it. I got it. Oh, it's fun. Here we go. I'll work on problem number 1. This is homework 6. I know you guys got other obligations. Homework number 6. Oh, homework 6, number what? Number 1. So we have a factory worker. He pushes a 31 kilogram crate a distance of 9 meters along a level floor at constant velocity, pushing horizontally on it. So here we go. You got yourself a crate. What do we say? 31.0 kilograms. He pushes it all the way over here to this. This is 9 meters. Change in x. 9 meters. The floor is level. Constant velocity. What's that mean? Yes, but what's that mean for? What is constant velocities? What's up? Yes. Acceleration 0. The what? The net force is 0. Also true. Very good. How about the work done by the net force? 0, right? In other words, the change in kinetic energy is also 0, right? Work energy theorem. All right. So you got some factory worker. I'll draw him as a Pac-Man for a change. And he's pushing the box with some force F. All right. Sorry, I don't really, technically speaking, I'm not sure if we can assign a gender to Pac-Man, but you know. Oh, there is Miss Pac-Man. But you know, from the modern perspective.
I think she's self-identifying.
Pac-Man, but I self-identify as a female Native American Indian. I mean, I don't know. It's ridiculous. Whatever. Oh, the coefficient of kinetic friction between the crate and the floor is 0.25. All right. This is a really, really hard question if it's frictionless. In some sense. I mean, like, it would be impossible if it was frictionless, right? If you push in the box with any force, if there's no friction, you're going to add kinetic energy to it, right? So it's a contradiction. Or you could say the force is zero. All right. This is the setup. Here we go. A. Magnitude of the force the worker must apply. Okay, so what's the complete free body diagram here? You've got what? You've got on the one hand, you've got the force of the worker, right? But you've also got the friction force. And while we're at it, I suppose you also have mg like this, and you've got the normal force upstairs, right? I mean, like that. And so we have N is equal to mg. And so the force of friction, which is mu mg, which is mu n rather, is actually equal to mu mg, right? Now we're given numbers here so we can plug things in. The force of friction is actually what? It's 0.25 times 31.0 kilograms times, sorry folks, it's a web of science, I gotta put 9.8 meters per second squared, as much as I'd like to put 10 there. No can do. It'd be nice if WebAssign had some sort of functionality where you can set the value of G for your course. But unfortunately, they haven't really thought of tailoring their physics instructions in the extrasolar setting. I mean extraterrestrial setting, I should say. See here, 0.25, like, what if you want to do WebAssign on the moon? You know? No one ever thinks of that. I get myself a 75.95 newtons. I'm just so excited that you guys understand this so well that you don't need to do homework. It's good. All right, let's see here. Force of friction, 75.95. Now, is that right? Well, I got a 76 here. Now, why? That's the force of friction. Why should that also be the force? Right. So MA is F net, which is also F minus the force of friction. So this tells us that the force is equal to the force of friction, which is 75.95. Okay. Does that make sense to everybody? I hope. Question B, how much work is done on the crate by this force? Yep. This is number 1 in homework 6. Oh man, really?
Remember you were saying you have all of them printed out?
Do I? So I have a different. Oh, that's my problem too. I'm sorry. Yeah, so I have the extended version of homework 6 that I'm working on right now. Sorry.
Is this number 1 a different number on homework?
No, I don't think this is even this is probably not even on homework 6 then. What's that? No, it's helpful to learn. Yeah. It's not a waste of time. I mean, these are like totally useful test questions. These are very useful test questions, right? And or just questions to learn physics. Let's forget about the test. I know you'd like to, and many of you, me too. But
wait, Professor, what was the
yeah.
last thing you read? You used like equals after equals after equals.
What? Oh, this?
Yeah.
75.95.
No, like between the break of the board. And
Oh, this? I was saying you can get from there to there. If you don't like this, you could use one of these guys. I'm saying that this implies that. Because, of course, as you guys told me before, this is 0, right? Constant velocity. So that means the force of friction and the force pushing has to balance. All right, so I lost track of who, yes, you'll keep me on track. So my number 2 is your number 1, is the point. I got a tugboat problem for number 2. We'll do that next, okay? If you want me to. Now, part B here was what? If you guys remind me, after the homework is due, all right? After it's, done, which happens before the test, right? I'm not pushing that due date back, by the way. I refuse. I saw what happened last test when I pushed it back. It did not help you. It's going to stay where it is. You must finish it by then. Make this class a priority to finish it by then. Speech done. Now, the point is, once that's happened, once the web assign is due, then I can post this extended one with all the answers. And that might be helpful to you. All right, so you'll actually have a PDF of this thing I'm looking at once that day comes. You do need to remind me to do that, though. I might forget. All right, how much work is done on the crate by the force? Should this work be positive or negative? So what's the work done by F? Is it positive or negative? It's positive, right? It's in the direction of the motion. It's constant, and it's lined up. It's the simplest thing. The work is just the force times the distance in this case. We certainly don't need a line integral for this one. So 9.0 meters times 75.95 newtons gives me a certain number of newton meters, which we also know as a joule. In fact, 684 joules of work is done. How about the work done by the force of friction? So this is the work of F. This is the work of the force of friction. What's that? It's minus, exactly. So it's minus 684 because the direction is opposite the motion. Right? The motion's this way, the force of friction's that way. They're diametrically opposed, so it's minus force times distance. That has to be, right? Because then the net work, all right, is the sum of the works done by all of the individual forces involved. There are 2 forces involved here, right? So whatever work is done by the force, the pushing force, has to be, let's say, undone by the force of friction, so that the net work can be 0. As we know, it has to be because we're given it moves at constant velocity. How much work is done by the okay, the last D, E, and F, I don't need to write anything. How much work is done by the normal force? 0. It's perpendicular to the motion. How much work is done by gravity? 0. It's perpendicular to the motion. What's the total work done on the crate? 0. All right. Very good. You guys want to see me work on the tugboat problem? Yes. All right. 2 tugboats pull on a disabled supertanker. Each tug exerts a constant force of tugboats. So let's say this is the supertanker. Very, very good picture. Let's see here. And each tug exerts a constant force of 1.5 times 10 to the 6 Newton, 22 degrees west of north, 22 degrees west of north. So one is pulling like this. I call that F1. Right? And the magnitude of F1 is, for me, it's 1.5 times 10 to the 6th newtons, aka 1.5 million newtons. And the other one is pulling at 22 degrees east of north, and it's also the same magnitude. Like so. right? So these, you have a tugboat pulling that way, another tugboat pulling that way. What else do we get? As they pull the tanker 0.63 kilometers toward the north, what's the total work they do on the supertanker? So it was down here, right? This distance is 0.63 kilometers. What is the work they do on the supertanker? So, all right. Again, no need for integration, right? This is a constant force problem. So what we have to do is find, so basically this problem and this problem all fall under the umbrella of this formula. The force dot the displacement is the work done. This is true for constant force. All right? So, basically here, I need to find, okay, so which part of these is not doing work? This piece and this piece, right? So we only need the vertical, let's say, components. We need F2y and F1y. Right, so what's the net force? The net force in the y direction, it's F1y plus F2y. How do you get those? Well, by symmetry, it's twice twice the first one, let's say, right? How do you get the y component? So what do you guys think? Is it a cosine of 22 or is it a sine of 22? Right, cosine because that is the side which is adjacent to the vertical direction given that angle, right? So cosine 22. So 2F1 cosine 22 degrees, that gives me the net force in the y, and then to get the work, again, it's the total net force dot the displacement, but that is, of course, 2F1 cosine 22 degrees times this d, right? I guess that would be, 630 meters? Fine, so I've got 2 times 1.5 times 10 to the 6th times the cosine of 22 times 630 Newton meters, aka joules. What is that? You can check me on that, right? I'll check me on that. How about that? Make sure I'm in degree mode. Yeah, 1.752 times 10 to the 9th joules. There you go. So do you guys see the general idea here is we have to identify if the work involved is constant, if the force involved is constant, what you have to do is you have to find the part of the force which is in the direction of motion, right? And then that component times the distance gives you the work done. Mathematically, that is entirely equivalent to saying you take the force dot the displacement, and that gives you the work done, because the dot product picks up the component of the force which is in the direction of d, right? You could rewrite this as F dot d hat times d if you wanted. That's exactly the component of the force in the d direction, and that's the length of d. So it may or may not be helpful to really think about dot products directly. I usually don't think about them for problems like this. I just think about finding the net part of the force, which is in the direction of the motion, and working from there. All right, let's see here. I'll look at number 3. I guess I'll leave number 3 to you guys. Let's look at number 4. The gender fluidity of Pac-Man. I never thought that would come up today when I woke up this morning. See, that's the thing about physics. It takes you all kinds of strange places. Homework 6, number 4. A soccer ball 0.425 kilograms is initially moving with a speed of 3 meters per second. Let's say horizontally. And let's call that V naught, okay? The soccer player kicks the ball. That's a foot. He kicks the ball, exerting a constant force of magnitude. He kicks the ball, force of the kick is 36.0 newtons in the same direction as the ball's motion. Over what distance must the foot be in her foot, I'm sorry, excuse me. So sorry. It's my upbringing. Eventually I'll learn not to be a sexist and assume that it was a male soccer player. I'm sorry about that. This has made this an unsafe space for you. I'm very sorry. I did warn you though that this wouldn't be a safe space though, right? I did warn you. Let's hear. So 36.0 newtons. Over what distance must her foot be in contact with the ball to increase the ball's speed to 6 meters per second? Okay, so at the end of the kick, for some reason, the ball is smaller, and it has a final velocity of 6 meters per second. The question is, this constant force over what delta x, what displacement do you need to have that happen? So how do you do this? This is like just straight up work energy, right? The change in kinetic energy, right, is equal to the work done. Now gravity and the normal force are not doing work here. They're perpendicular to the motion. We can neglect them. All right? Friction is also negligible because this has happened very fast. We're ignoring friction. We don't know what it is anyway. All that really matters, of course, is the force of the kick. And so the force of the kick is constant. That's nice. So we can just say it's 36.0 newtons times delta x. That's the work done. It's a positive work too, right? Because it's in the direction of the motion. So what's the change in kinetic energy? Well, we got that too. 1/2 mvf squared minus 1/2 mv naught squared. So do you see how to go from here? So we solve for delta x, right? Multiply by 2, I guess. So I've got, and factor out the m. What is m? 0.425 kilograms times 36 minus 9 divided by 72. I'm working in kilograms, meters, and this is going to work out to meters when I do the units right. Whatever that is. Ooh. Jerk move by the webassign. Watch out for this one. They'll get you. They're like, haha, student minding his own business, enjoying his life. We'll teach him what's what. He'll work this thing out. He's going to get, I'm sorry, he or she might get 0.159 meters and go, aha! Answer, I made it into 72, multiply by 2. You know, and then it will not give you the delightful green check. It will give you the dreaded red X. No, what's wrong? What's wrong? And then you go, oh, centimeters. Yay. So 15.9 centimeters. And then, yes. So don't let WebAssign steal your joy. Put it in centimeters to start with. Okay. I'm bored of these problems. Let us jump ahead. How about, something about a bricklayer shooting bricks. That looks interesting. Number 8. Oh, I'm sorry. Gentleman by the camera. My interpreter of numbers. Uh-oh. Hello. I need an interpretation. An ingenious bricklayer builds a device for shooting bricks to the top of a wall he's working. Is this existing in our homework set? Which number is that? Number 5? Oh, okay. Oh, man, I got rid of a bunch of them. So I already got rid of 3 of these. Well, no wonder you guys aren't doing well in the test. I didn't give you enough homework. Should I go change it? I could change it. I could add problems. No? No? You say unless I change due date. I am, of course, just being facetious. You can also gain an unfair advantage by working problems at the end of the chapter. I've also heard that there's instantaneous feedback with odd problems in the back. There's this thing called the back of the book, and there's answers there. And, well, it's not entirely instantaneous. You do have to turn the pages all the way to the back and look at the numbers, so it takes some time. But not much. Where was I? An ingenious bricklayer builds a device for shooting bricks. This sounds awesome. To the top of the wall where he's working, he places the brick on a vertically compressed spring with a spring. It sounds like the start of a lawsuit. Let's see here. All right, so he's got the brick here. And so this spring has a spring constant of K equals to, where was I? 380 newtons per meter. All right. And the spring has negligible mass. When the spring is released, boing, the brick is propelled upward. And if the brick has a mass 2.0 kilograms, it reaches a maximum height right here, all right, of, I think it says 4.0 meters. 4.0, where was I? 4.0 meters above its initial position. All right. What distance must the spring be compressed initially? The brick loses contact with the spring when the spring has returned to its uncompressed length. Why? All right, so let's answer the question here. So what do you do? I mean, it's pretty simple. The point is you initially press the spring down, right? And you give energy to the system of 1/2 K change in X quantity squared. Or I could just say X squared, I'm sorry. 1/2 Kx squared. This is the potential energy of the spring. The initial potential energy, and that's equal to what? There's no kinetic energy, right? Yeah, and why would that? So up here at the top, again, the final velocity is also 0, but the potential energy is gravitational, right? So yeah, E equals mgh is the way to do it. And I think we have everything we need because we've got m, right? We got K. We've got H. H is 4. We know G. So we can solve for X. So we get 2 mgh divided by K, square root of that. So 2 times 2 times 9.8 times 4 divided by 380, square root that thing, meters. Of course, who knows, maybe they made us put it in centimeters again. Nope, meters. That's quite a spring. That's a very big spring, right? Spring. I think the spring is taller than some of my children. I don't know. And they're not that small anymore, so you're... Let's see here. Stupid. 0.642 approximately meters. Yep. Can any of you guys explain why the brick loses contact with the spring when the spring has returned to its uncompressed length? Right, so like at a slightly later stage, the spring is back to its uncompressed length, like say here, all right? So x is equal to 0, let's say. And then the brick is going up with, let's say, velocity v1. Why does it lose contact with the spring?
It accelerates down.
What?
It reaches its max velocity and then starts accelerating. It also puts a crap load of force in there.
I mean, yeah.
Is it kind of like the same principle with like our seatbelts? How like whenever we stop our car, our bodies still go forward, then the seatbelt pulls us back?
So your answer is inertia, basically? Yeah, I guess there's nothing holding the brick down, right? Except what? Gravity, but since energy is conserved, we know it has a non-trivial velocity going upward, right? So, I mean, if it's got velocity, it's going up, so it's not going to stay there. Trying to think of how else to explain this. I mean, while it's still on the spring, of course, the force of gravity is pushing down on the spring, and the normal force is pushing back, right? But, anyway. All right, any other one you guys have a specific question about? Yep.
Can't you figure out like how I goes based on like the force that the spring is putting on the thing? You multiply 380 by the distance that it compresses.
Well,
That's the force up, and then
see, but it's not a constant force here, though. You see, because the force is governed by Hooke's law, minus kx, right? Or maybe y would be better here. I don't know. I mean, already using x, but so that's not constant. I can't just take force. Which force? The force when it's compressed, or the force when it's at 0? Well, that's the maximum, and then it decreases to 0 over the motion. So it wouldn't be fair to just take the initial compressed force times the distance, because it's not a constant force. You have to integrate. I mean, technically speaking, you'd have to integrate from, say, what did we figure out? 0.642 to 0 of minus kx dx. This would be the work done by the spring. And of course, this is, minus 1/2 kx squared, evaluated from...
would that be a negative point?
No, it's compressed.
So, okay. Do you consider...
Oh, wait a minute. Wait. Yeah. You might be right. Let me think about that. You're correct. Yes, it should be negative 6. Thank you. But that said, it's hard to... Doesn't matter. The square eats it anyway.
Well, you got an original negative as well, on the 1/2.
That's from the integration of minus kx. Oh, this is because fundamental thermocalculus, top minus the bottom, so minus minus gives me plus.
Oh, right.
Sorry. And then K is what?
380.
What does this give us? What? Oh, I forgot the square. I'm sorry. I'm an idiot. Yeah, 78.3. You are spot on. 78.3, what? 78.3 joules. Now calculate for me, what is mgh equal to? 2 times 9.8 times 4, what do you get? Well, what do you know? What is the mysterious connection between these numbers? I mean, an approximation error, right? These are the same number. Yep. Right, energy is conserved. In other words, the work, so basically what we're seeing here is the work done by the spring in putting the brick in motion. Basically, it's like a gun of some sort. It launches the brick with initial velocity v1. According to this amount of work being done, all right? That work is initially, all kinetic energy, all right? And then it goes up 4 meters, right? And then that kinetic energy is converted into gravitational potential energy at its highest point, and it falls back down, right? But you see, we have to do integration in order to understand the work done by the force, because it's a variable force. See that? I dodged that question in my first treatment of this problem because what did I do? I used the potential energy concept, right? This is the potential energy of a spring. So by using this, I don't have to integrate the force. I've already integrated the force to come up with this as a means of understanding the energy that's stored in the spring, which is the same energy that the spring force does work by. Any particular one you guys want me to do? So here, I'm going to move on then. I think these are all more or less the same kind of thing. Oh, here's one. Do you have the hammer of a pile driver weighs 3,600 newtons, blah, 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 blah? You don't know? All right, tell you what, forget about the homework for a second here. Let me just communicate to you guys a general principle of the physics. What is power? We talked about work, we talked a little bit about energy. So if I have work, right, if I calculate the work per unit time, this is equal to the power developed by the force, which does work, work W up to time t. All right, so what I'm trying to say is you've got a force, all right, F, let's say. It's doing work. And you want to measure at the rate at which it's doing work. How many joules per second is it developing? This is called power. All right, definition of power is this. So what's the formula for it? So what's the work? What's the work? The work, right, is the integral, say from t naught to t, of f of, let's say, tau dot, dot the velocity, right, d tau. That's a formula for the line integral. And I just use tau as an integration variable because I want to think of t as a fixed but arbitrary time that I'm trying to measure how much work has been done by that time. And so to calculate dw dt, what do I get? What happens when you differentiate an integral with a variable bound? Nothing? Did somebody say nothing? Sort of. It undoes it, right? Fundamental theorem of calculus part 1 says that this derivative is the natural enemy of that integral. They vanish, and they just leave you with f at time t dot with the velocity at also at time t if you want to be specific. Or just to eliminate the time dependence, you could just say f dot v. So there you go. There's your go-to formula. If you want to calculate the power developed by a force on some body which has velocity v, what you do is the force dot that velocity gives you the power that's being developed. For example, immediately you can see that the power developed by forces perpendicular to the motion is what? It's 0, right? Normal force, for example. So there are a few questions in your homework about like, what's the power developed by some force? All you got to do is calculate the force dot the velocity. That will give you the power which is developed, okay? So this is an important formula to know about, concept to be aware of. What happens if you integrate the power over time? If power is work per unit time, and you integrate it over time, what do you get? Work, right. In other words, another way you could look at the definition of work is it's the integral of the power. If you took power as a more fundamental thing. And you might. All right. I'm going to go on to homework 7. Oh, it's energy analysis. Well, I mean, that doesn't mean we can't solve it, though. Let's see here. A mailbag. This is my number 2. I don't know what it is of yours, though. Homework number 7, possibly number 2. I'm not sure. A mailbag with mass of 130 kilograms. It's a strong mailman. Is suspended. All right. By a vertical rope 6 meters long. All right, so we got a mailbag hanging on a rope 6 meters long. All right. The question is this: what horizontal force, all right, is necessary to hold the bag in a position displaced 5 meters from its initial position? Five meters sideways from its initial position, I should say. What's that mean? Five meters sideways means what? This distance is 5 meters, right? So it's been pushed over to like here, right? You could judge everything by the center of the mailbag. I'm just using the base of it as a point of reference. Just pick the same point of reference. Okay. The dimensions of the mailbag don't concern us. So that's 5 meters. The question is, what horizontal force is necessary to hold the bag in that position? And then part B asks how much work is done by the worker in moving the bag to this position. Part B is an easier question. How much work does it require? It starts at rest, it ends at rest, right? So what's the difference? Is here it has, if we take potential energy to be 0 down here, right? Suppose this is H equals to 0. So in other words, potential energy initial is 0. Then at the end, right, we have, say, HF. So this has the final potential energy of what? MGH, right? I guess I called it HF. So that you could figure out, right? Because that's the work done as well, right? The worker has to do work to get it to go over to there. Basically, all the work they're doing is just creating potential energy due to gravity. The other forces involved don't do work, like the tension of the rope is always perpendicular to the motion, so that doesn't do work. So gravity is the only one that you're working against by pushing it. So that's anyway. This is the work done. Going to be the work done by the worker. What's HF though? How did you get that?
I kind of made the angle between the rope theta, and I said sine of theta equals
This?
Top left. Or
This
theta.
one here or that
Yeah.
one?
Left.
Theta, yeah.
And I said sine of theta equals 5/6.
Well, hold on a second here. Sine of theta.
Or you can do
No, that's not true. Oh, wait a minute. I take it back. You are correct. I gotta draw another triangle to see what you just saw, which is you could move the 5 up here, right? Then you're like sine theta is 5/6. Yeah, I'll buy that. That's a right triangle. That's the hypotenuse. That's the opposite side. Okay, then what?
then cosine of theta. Well, then once you solve the theta,
Uh-huh.
then you just can do cosine of that is equal to HF/6.
Let's see here. So you're like, well, okay, so 6 times cosine theta is this distance, right? So you do, I think you do 6 minus 6 cosine theta, right? Because 6 cosine theta is this distance. The total distance is 6. So 6 minus that distance gives me this distance.
What exactly is the problem asking for the final height? Sorry,
The problem is, no, it doesn't give it to you. The problem is just asking you how much work it takes. How much work is done by the force to get it up to that position. Now there's another way you could calculate it, right? You could just take the horizontal force times the displacement. That should also be equal to this number. Let's see if it is. So what did you guys get for the theta? I mean, what's HF? Can you calculate this for me?
2.68.
So 2 point, what you said, 2.68?
Yeah.
And so the potential energy final is what? 130 kilograms times 9.8 meters per second squared times 2.68 meters. What do we get? That should be the work done. I get 3,414.3 joules. All right. My suspicion is that well, I can check. Say, check yourself. All right, fine. I got 3,420 in my my answer key. That looks promising. Now, what was the force required, though, to keep this in equilibrium?
What was the force required to keep it in equilibrium?
Yeah, right here. Oh, I'm not sure I should assume that same force was applied. Am I supposed to assume the same force was applied over the whole deal? Doesn't tell me that. It just says what horizontal force is necessary to hold the bag in position, as pictured. All right. Anyway, so how do you find that force? What are the other forces at play here? How about the tension, right? And what else? Gravity, yeah. And the sum of these forces is what?
Zero.
Right. And let's see here.
Why'd you say
See, they shouldn't let me teach this course. I'm really not qualified. I mean, I hardly know any physics. I mean, I only have a master's in physics. I don't know if you really should trust me. Look at that. I just wrote an H where it doesn't belong. Sorry, I digress. No, the theta, where's theta in this picture? It matters. Theta is also here, right?
It's off the horizontal from 180.
Oh. That thing?
Yeah. I mean, we can also picture theta here. So this would be t cosine theta, and this guy would be t sine theta. So I have, on the one hand, t cosine theta is equal to mg. On the other hand, I have t sine theta is equal to f, because they have to balance. So I don't really care what t is. How do you get rid of it? Divide, right? So I'm going to divide this way. I get tangent theta. I'll get out of the way here in a second. I get tangent theta is equal to f divided by mg. That's a neat formula. But you know theta. Oh, so f is equal to what? mg tangent theta. I guess I need to be more careful with the wording of my problems on the next test. See, I allowed a loophole for you guys to drive a Mack truck through on this last one. I had this problem with the 18 meters and then fire it at an angle, find the range. And a couple of you just wrote that greedy formula I derived in class and just plugged numbers into it. And I had not guarded against you doing this, and I had to give you points. And it's very bothersome to me because you did no physical thinking whatsoever. You completely just bogarted my solution. I mean, it's good studying. Don't get me wrong, it's good studying. But still. Cotangent. Cotangent.
Yeah.
No, and then you flip it.
What was the angle? I don't know. Oh, if sine theta, oh, this is more fun. If sine theta is 5 over 6, what's cosine theta? Cosine theta is the square root of 1 minus 25 over 36. Waha. So this is mg 5 over 6 divided by the square root of 1 minus 25 over... Well, I don't know why I'm doing this. You could just use a calculator. Let's use a calculator. Forgive me for this. I have to turn off my calculus 2 brain for a second here. What was the angle? Sine inverse of 5 over 6, right? This is, theta is what? Theta is equal to 56.4 degrees. So m, what was m? 130 kilograms times 9.8 meters per second squared times the tangent of 56.44 degrees equals to 19 stupid divider. 1920. I got 1920.6, but I wouldn't say that last decimal is terribly significant. And what are we doing? Newtons. Yeah. Interesting. So, question. If you take this force, right, multiply it by the displacement. That force is in this direction, right? What's the displacement in that direction? 5 meters. If I were to take the displacement vector, which would be this guy, right? And if I was to take this force, if I was to take F equals to, 1920.6 newtons x hat, right? If I was to take this dot that, what would I get? I would get 5. I would get 5 times 1920 joules, which would be what? $9,603 joules. Oh, man. And maybe that's what you would have done if you fell into the trap of this problem. See, because this problem asks you, part A, find the force that keeps it in equilibrium, right? Part B, find the work done by this force to make it so. Some of you would have done what we just did. Multiply 5 times the force, right? Even I was starting to get suckered into this until I thought about it a little bit more. Why is it not valid? Yeah. No, I mean, I can still ask the question. There's getting towards it. What is that? Right, that is the force that's necessary for equilibrium. It is not given to it. If you were to exert that force on the body horizontally over the entirety of this motion, like that, it would not be at rest at the end. It would have non-trivial velocity. You would have done work by the kinetic energy theorem, and it wouldn't match the parameters of the problem. In order to get the thing up to here, you have to, at the start, push on it, I think, less. And as you move further and further over, it takes more